Hello and welcome to another Arlington High School Math 4 Honors lesson. My name is Kirk Weiler, and today we're going to be doing Unit number 12, Lesson number 2 on level curves. Before we even get into the topic today, it's important to kind of understand that when you are in single variable function work, f of x, that there are particular tools that you use to analyze the behavior of these functions. Some of them are sort of simple, like intercepts or even just the graphs of the functions that you can produce by hand. Some of them are more challenging, like calculus, where you can look at slopes, instantaneous slopes, and concavity. In multivariable functions, there were a whole host of tools that were developed historically because we didn't have the ability to graph these things easily. There's certainly technology now, we saw it in the last lesson, that allows to graph these surfaces. But we're going to look at one of the primary tools today, and it's what is known as the level curve. So let's jump right into it with an example, or with a definition. Sorry about that. The level curves of a function. The level curves of a function f of two variables are the curves with equations f of x comma y equals k, where k is some constant in the range of the function f. Okay, what? All right, well, graphically, this is what we're getting at. Here in red, we've got some surface, right? And what we've done is we've taken a surface with constant z value. That's that blue thing. It's a plane. Maybe I shouldn't use blue ink. Maybe we'll go to green. It's a plane, and the question is, when we intersect this surface with this plane, what kind of curves do we get? In this case, we get a curve there, and we get a curve here. All right. Actually, we get a hyperbolic curve or a hyperbola curve. That's what's known as a level curve. And it's very simple. It's a curve in the xy plane where all along that curve, if you were to walk along it, if I was like taking a little walk, strolling along this curve, right, just kind of walking along it, what I would see is a constant z value, constant z. Nothing like this really exists when we analyze functions of a single variable. I mean, it might be interesting to know where we have sort of repeated y values, but here we're talking about entire curves that if we walk along them, we will only see the same z value. And they are very, very powerful. Some people might call them cross-sections. Some people might call them contoured curves. And that's probably the second most common name. Now, a purist might disagree with me and say, well, contours aren't the same as level curves. I would say that they were being overly picky. All right? A contour, right? Like a contour map. If you've ever seen one of those as a hiker, you might see a map where all these things have constant elevations, right? That'd be a beautiful picture, I'm sure. All right, I'm going to clear all this out, and then we're going to start to analyze some functions using level curves, okay? Here it goes. All right, moving to the next problem. Okay, exercise 1. Consider the function f of x equals x squared plus y squared plus 1. All right, so what we want to do is we want to try to analyze what this thing looks like, how it's behaving, using some tools that we already have. First question, what's the domain of this function? What kind of x, y coordinate points can we put in this function and get a value of z out? Pause the video if you need to think about this. Seems to me that we can put anything in, right? So we can really put anything in. Well, that means that the domain is the entire xy plane. When you were talking about f of x, sometimes you had functions where it was the entire x-axis. Now we're talking about the entire xy plane. So when I graph this thing, excuse that little thing there, and I have my z-axis and my x-axis and my y-axis, I can take any point in this plane and I'll get a z value. Now the range is a little trickier. I really want you to think about this. Now remember, the range is all about the values that z can have, the values the output can have. So think about that a little bit. All right. Very often, just like functions in a single variable can have a range that's all real numbers, we can have functions in multivariables that also have ranges that are all real numbers. Not in this case, but very often. In fact, one could say that the range, let me write it in set builder form, is all values of z where z is greater than or equal to 1. All right, think about why that is. If you look at this expression, x squared plus y squared plus 1, this portion of the expression must always be greater than or equal to 0. I mean, test it with values, think about it logically. If I square x and I square y, the smallest they can be is 0. I wish I could say that they're positive, but not necessarily. So since that part is always greater than or equal to 0, the overall function must be greater than or equal to 1. Why don't we just get rid of that? All right. Now it says describe the level curves of this function in as much detail as possible. So here's what I suggest to people when they first think about level curves. Now remember, the idea is I want to know all the curves where if I walk along them, I hit the same z value. So the z values are all greater than or equal to 1. So how about this? Let's think about this level curve. All right. So now I want you to understand this is all points x comma y in the xy plane. All right, so we're living down here, that give a z value, I know that's a little tricky, of 2. Right, that's all we're doing. Hey, give me all the things that make this expression equal to 2. What is that? That's x squared plus y squared equals 1, right? If I subtract 1 from both sides, so it's a circle. All right, in other words, if I'm looking at the xy plane, right, and I travel on this circle, travel somewhere on this circle, then everywhere z will be equal to 2. Everywhere on that circle, not on the inside, but if I were at this point, whatever it is, z would be 2. If I were at this point, z would be 2. This point, z would be 2, right? Now that's just one particular level curve. That's the level curve that gives me z equals 2. On the other hand, I could go a little more generic. I could say, well, let's say I pick a generic z value. For whatever reason, very often they use the letter k. So I'm going to say this is a generic z value. I know, kind of why don't we use z? Well, we don't. And of course what we get, there's the bell again, me and my timing, is we get something like this. And this is also a circle, right, with the center at 0, 0, and with a radius equal to the square root of k minus 1, right? So every level curve on this surface is a circle centered at the origin 0, 0, not the origin 0, 0, 0, although that would actually be true. And we know that the radius depends on the z. In fact, as k goes up, right, as the z value goes up, the radius goes up. All right, really kind of cool. All right, we'll look at some of these curves later on. For right now, we're going to skip the fancy schmancy programs, and we're going to just go on and keep thinking about what's going on. I like to talk to kids about level curves in terms of Catscans, because we all have experience with those, right? Catscans or MRIs basically work by slicing a three-dimensional object like a person's brain. I mean, they're not really slicing the brain, but they're sort of slicing it with a picture, right? And they're coming up with all these cross-sections, and when they put the cross-sections together, they can figure out what the actual solid looks like. So if I know the cross-sections are all circles, it gives me an idea of what the overall solid behaves like. Okay, we're going to move on to the next exercise. Describe and sketch some level curves for the function 4x squared plus y squared. 4x squared plus y squared. All right, well, just as a side note, it's good to note that the range of this thing, right, is z greater than or equal to 0. right? So that's good, because that means we can start with all sorts of things, right? We can say, well, let's take a look at what happens when z is equal to 1, right? What kind of points give me this? Well, hopefully everybody realizes that this is an ellipse, right? In fact, we can sketch this ellipse. That is a beautiful looking xy axis, right? This would be an ellipse whose x-intercepts would be 1/2 and -1/2. Think about that. And whose y-intercepts would be 1 and -1. So all along this curve, beautifully done, all along that curve, if we walked along it, then we looked upwards, all along it, we would say the same z value. We'd see a z value of 1, right? Now we have to be a little bit careful, otherwise the math is going to get awfully ugly. But you could also think about, let's say, this one, where z is equal to 4, right? In this case, we also have an ellipse. All of these end up being ellipses, all right? Here, the x-intercepts are -1 and 1, and the y-intercepts are 2 and -2. So all along this curve in the xy plane, anywhere on this curve, we'd hit a z value of 2. In fact, if you were looking at a topographic map, right, these elevations would be listed. They typically are not listed on a contour or a level curve graph. I don't know why, because they're a great idea, right? Z equals 1, z equals 2. You know, we could, oh, I'm sorry, that's not z equals 2, that's actually z equals 4. I apologize for the confusion. All right. Eventually, we're going to know this surface as being what's called an elliptical paraboloid. An elliptical paraboloid because its cross-sections, horizontal cross-sections, or its level curves are all ellipses. All right, but we'll look at that more in a later lesson. All right, I'm going to clear this out. Here it goes. All right, let's do a little matching exercise. How often do you do this? All right, in exercise 3, and I know this is laid out differently on the worksheet, I apologize, not to mention the fact that you don't have the color on the worksheet. But what I've got is I've got 4 surfaces. Now, on the worksheet themselves, there's equations of those surfaces, but here I didn't give them to you. And what you're supposed to do is match the surface with the level curve graph. All right, now it's a little bit tricky, especially when we can't like rotate and revolve these things. We're going to do that in a little bit. But the idea would be if I took something and I cut this surface with a horizontal plane, you know, if I sliced it with a horizontal bread knife, you know, now remember that z equals a constant. You know, which one would give me the level curves? May be obvious to some, may not be obvious to others, but it would be something like this. All right, all of those cross sections are circular. On the other hand, this little guy, which looks a little bit like a potato chip, right? If I cut this thing horizontally, again, less obvious, I'd get something like that, and I'd get something like that. That's this guy. Eventually, we're going to give this thing a name. We're going to call it a hyperbolic paraboloid. Now, these two are a little bit tricky, you know, which one's which. This one, with all of those bumps, all of those maxes and mins, actually goes with this. You can always tell a three-dimensional max-min on a problem because what you'll see are things that essentially look like concentric circles, even though they may not be, right? And likewise, this one then matches up with that guy. Okay. Strangely enough, that's actually it in terms of the lesson. But let's play around a little bit. I'm gonna clear out all of this because I want to show you a couple of these, specifically what we're going to do, because again, I think it's just necessary because it's cool. So we're going to take a look at that one, and we're going to take a look at that one in a second on our grapher. Okay, so I'm going to clear this out. Gone. And moving on. Okay, so some cool exploration. So at this point, let me open up the one that's got that kind of almost like ripple-like effect. I'm going to open up Grapher now. All right. Isn't that kind of neat? Now, It's really rather cool. You can zoom in and out on these graphs. Grapher is not the best about that because it won't let me play around with the z-axis. So when we zoom out to see more of it, unfortunately, the z appears to get compressed. But let me do that. Let me zoom out. And let me zoom out again, right? And I think especially in this last view, you can definitely tell how the waves have kind of like got damped out over time. This isn't the exact equation that's on the sheet, but it's good enough. And it's awfully neat, especially when I zoom back in. You know, you can really tell how that thing kind of undulates outward. It's sort of like a three-dimensional version of a damped oscillation, right? A ripple moving out in a pond, if you will. Okay, so that one's really, really cool. Let me do something really quick. Let me turn on what are called the contours of the graph, all right? The contours are, again, they're going to be lines that circle the graph that have constant z values. So let me go to that. Turn on the contours. Get back out. And now you can really see them, you know, especially if you rotate the graph so you're looking down right from above. You can really see those circular level curves, all right? And that's exactly what we have here. I'm going to close this one out. And I'm going to very quickly open up another one. All right. And this next one is my friend the Pringles potato chip, the hyperbolic paraboloid. It's so neat, you know. Again, just rotate it to get some feeling for the surface. Okay, kind of neat. What I'm also going to do is I'm going to look at the those contour lines. So I'm going to go up, turn on the contours. There it is. All right, let me get out of there. All right, look at that. Now again, doesn't show you much when we're sort of in the side view, but if we rotate it so we're looking right down from the top, there are those hyperbolas, all right? So it's really kind of neat, All right, rotate it back and close it out, and I've almost lost all of my memory on my disk. Anyway, I'm going to finish up. I don't want to lose that entire thing. I'm going to hit OK here. Hopefully hit OK. You're now seeing the inner workings. Maybe I can get back in here and finish it up. Okay, it's going to give me a little bit more room. So let me finish up now really quick before I run out of memory. That's still not the right title, but we'll finish up anyway. So let me remind you that this has been an Arlington High School Math 4 Honors lesson. My name is Kirk Weiler, and until next time, keep thinking and keep solving problems.